First, this paper is very technical and unusually for a KI paper does not actually contain an empirical user study. But just to make the point that the system that we are talking about in this paper is not just theoretical. We have implemented a complete system and it was demonstrated on BBC Click Live by one of the co-authors of this paper, Professor Annalu, who can be seen in this photo having our system running on a tablet on her lap. AAC methods allow people, non-speaking individuals with motor disabilities, to communicate. There is unfortunately a very large communication gap between people speaking normally, using rates, achieving rates between 125 and 185 words per minute, and people using AAC who typically meticulously type their sentences on a tablet or physical keyboard and then have their sentences read out by speech synthesis. Typical communication rate for such aided communication are in the range of 8 to 10 words per minute. It is possible sometimes to accelerate these rates using various acceleration techniques to achieve entry rates between 12 to 18 words per minute. And there are also exceptions of people who may achieve higher or even lower entry rates. In general, individual rates span a very wide range, as every individual has their own unique abilities and challenges. The fundamental idea in this paper is that we can improve AAC communication rates by using what we call context-aware sentence retrieval. And context-aware sentence retrieval has two components. The first component is the sentence retrieval component. A side effect of low entry rates in AAC is that a lot of AAC users often store commonly used sentences or phrases in a sentence cache. Access to this cache, however, is typically tedious using various hierarchical access mechanisms. Our solution is to seamlessly integrate sentence prediction along with word prediction, which people are already making use of when typing on a tablet, for example. So as the user is typing, not only does the system predict words, but also sentences. And these sentences are predicted based on the sentences stored in the individual user's sentence cache. The second component is that we have an hypothesis that we can improve efficacy even further by making use of contextual information, such as the speaking partner, the speaking partner's name, time of day, or, for instance, the geographical location the user is situated in. We therefore automatically add what we call context tags to the user's input. And a context tag is a label that describes aspects of the context of a conversation, such as the location, current time, or conversation partner. We have built such a system, so we have built a context-aware sentence retrieval system, and I showed it to you in the photo in a couple of slides before. It's been used for a prolonged amount of time by a single expert user. However, we have a challenge here, and the challenge is for the system to demonstrate efficacy. It needs to be tested for a prolonged amount of time in a large heterogeneous user group. And there are four particular problems here. One is what we call the bootstrap problem. The system needs to learn individual sentences communicated by the individual, and up to 6 months of use may be required in order to accumulate enough sentences for the system to demonstrate true efficacy. The second problem is the logistics problem. Having even a single AAC user and their assistant, family, friend, or other people switch to a new device for the eventual benefit of a hypothetical system is very, very difficult and maybe even ethically wrong, because we cannot be sure that our system is actually better than the system that it's replacing for these 6 months of use, which we may demand a user to test our experimental system for. The third problem is the surrogate data problem. Preceding existing sentences has to rely on assigning context post hoc, and these context tags that are assigned post hoc are unlikely to be valid. And the fourth problem is the proxy user problem. Using people pretending to have dexterity issues cannot replicate what we observe in users who have involuntary or idiosyncratic movement. So it's really difficult to evaluate this system. Our approach, and that is the second contribution of this paper, is to introduce a design and engineering approach as a complementary design methodology for AAC. In design engineering, we are borrowing a specific phase in design engineering called conceptual design. In this phase, the system is decomposed into its critical functions. These functions collectively become the system's function model. Once the function model is known, we can then investigate function carriers. They act as solutions which we can use to implement these functions in software or hardware. Parameterizing the function model allows us to study the performance as a function of the design parameters of the function model. We will call this envelope analysis. Such envelope analysis can help guide design because it shows us what is indeed possible to achieve, and it can help identify requirements, it can help identifying design parameters that can be optimized, or in general, it can help us to understand how well a complex system is behaving under varying operating conditions. The process is a 6-step process. In our approach, we construct a model. This model randomly samples a sentence from a set of 500 representative AAC sentences. The model simulates a user typing this sentence with or without support of autocomplete word prediction. Each word is added to a bag of words, either typed or auto-completed, depending on the analysis we are doing. If context tags are available, these context tags are immediately added to the bag of words. When a word is added to the bag of words, the system performs the sentence retrieval using one of 3 implemented information retrieval algorithms that are presented in detail in the paper. Unless otherwise stated, 4 sentence suggestions are shown to the user. The performance metric we investigate is called keystroke savings. It is the percentage of keystrokes saved when typing an intended sentence. Note that this metric is invariant of time performance. We're not trying to predict how quickly people are able to type using context-aware sentence prediction. We are only assessing what percentage of keystroke savings can be saved using this system. In our function model, we have parameters, as I previously mentioned. These parameters can be categorized into controllable and uncontrollable parameters. A controllable parameter is a design parameter we can tune or improve, such as the number of context tags the system attaches to each sentence retrieval query. An analysis of controllable parameters allows for design optimization. Uncontrollable parameters are emergent system parameters we cannot directly influence in our design, such as the accuracy of the context tags, which depends on many factors, including the algorithm, the individual behavior of the user, and the context itself. Envelope analysis allows for an understanding of how sensitive the design is to factors we cannot directly control. In the paper, we'll list and evaluate a range of these parameters. And they are important because understanding their performance implications can help guide the design. In a short presentation, it is infeasible for me to go through these parameters in detail, but they are described in detail in the paper. And for interested listeners, I refer people to the actual paper. In what follows, I am going to show a couple of highlights from the envelope analysis. The first is a baseline analysis, where we are using no context tags and no word autocomplete. And what you are seeing is average keystroke savings as a function of the number of sentences available. And what you can see here is that if we present only the number 1 sentence suggestion, we can expect an average keystroke savings of about 50%. And it doesn't seem to matter much which information retrieval algorithm we use. As we increase the number of sentences made available to the user, keystroke savings increase. However, there is an obvious trade-off between the screen real estate and the time demanded for the user to linearly scan all of these sentence suggestions. If we enable context, so this is enabling 2 context tags and no autocomplete. And what you can see here in this figure is average keystroke savings as a function of the probability of correct context tagging. If we have 2 context tags and they are 100% accurate, we can expect 90% average keystroke savings, which is a substantial reduction. In practice, 100% context tagging is probably unrealistic. But if we reduce the probability to about 80%, we can see that we can still achieve a substantial amount of average keystroke savings. This slide is showing the role or the effect of autocomplete, word autocomplete. The left figure is showing average keystroke savings as a function of word prediction accuracy with 2 accurate context tags. So this assumes the 2 context tags are 100% accurate. As you can see, if we assume a word prediction accuracy of about 80%, the average keystroke savings in this case are 96%. If we look at the same 80% data point in the figure to the right, but assume that there are no context tags, we can see that the average keystroke savings reduced to 80%. So, we have observed that under reasonable parameter assumptions, substantial keystroke savings can be achieved by retrieving a stored sentence using standard information retrieval algorithms. And word prediction further improves the performance. The reason we can have these substantial keystroke savings is because we are retrieving sentences that are already stored in the system. Such retrieval is common in ASC and is therefore motivating the analysis. However, we also investigated the performance of typing sentences that are not stored in the system. Now, since we are trying to identify sentences that are not stored in the system, the sentences we retrieve are never going to exactly match the sentence the user is actually trying to type in this instance. We therefore define a tolerance threshold using word error rate. We use a word error rate tolerance threshold of 50%. That means we count a sentence as reasonably okay if at worst every second sentence in the retrieved sentence is incorrect. Here we can see the effect of trying to retrieve unobserved sentences in the system. Again, we see average keystroke savings as a function of the probability of observing a sentence. If we choose the midway point of, let's say, 50%, where the probability where on average every second sentence we try to retrieve is stored in the system and every second sentence we try to retrieve is not stored in the system, we can expect keystroke savings ranging between 40 and 60%. Many non-speaking individuals with motor disabilities rely on word prediction and simple sentence mechanisms to communicate. The communication rates are typically very low. We suggest a context-aware sentence retrieval model that leverages the fact that many AAC users reuse previously typed sentences. In our model, the user starts typing a sentence as usual, but is in addition to word predictions presented with a number of retrieved previously typed sentences. This model is difficult to evaluate or co-design directly with end users. Instead, in this paper, we suggest an approach from design engineering, where we identify the key functions and their controllable and uncontrollable parameters. This allows us to perform envelope analysis that can inform requirements, identify design parameters that can be optimized, and provide an understanding of how well the system can operate as a function of a number of factors we cannot directly control. The key message in this paper is that a design engineering approach involving identifying key functions and their controllable and uncontrollable parameters allows for a quantitative exploration of potential user interface design improvements without forcing AAC users to use untested systems for a prolonged amount of time. This complementary approach allows us to explore adventurous user interface designs that demand high upfront investment and are difficult to evaluate with AAC users. They enable us to reduce the opportunity cost of not exploring challenging potential solutions. The overall findings are that context-aware sentence retrieval is likely to realize substantial keystroke savings ranging from 50 to 96%, depending on assumptions on word prediction accuracy, accuracy of context tagging, and the level of sentence reuse.